Okay, since this is a calculus class, we should probably discuss the derivative of an exponential function. And what we want to do in this, I guess it's not really an example, it's almost more of a proof, but we want to use the definition of the derivative to calculate the derivative of, I guess, a generic exponential function of base b. So the first thing we should do is we should probably write the definition of the derivative. So the definition of the derivative. And we learned this in our first semester calculus class. That's going to be the limit as h goes to 0, f of x plus h minus f of x divided by h. So just a quick reminder in case you forgot, this guy is basically like a slope type thing. So the numerator measures the change in the y values with a small difference of h. And the denominator measures a small change in the x values. If you took x plus h minus x, you would get h. So this guy is really, it's really a slope-looking thing. It's really like delta y divided by delta x. Okay. So for us, our function is going to be this b to the x. So when we calculate f of x plus h, what that means is I'm going to substitute in an x plus h anywhere I see an x. So let's do that. So substituting, we're going to get the limit as h goes to 0, b to the x plus h minus b to the x all divided by h. Now, at this point, we got to remember we had just seen the law of exponents. So we're going to use the product one. So the product one was when you had two things where you have the exponents that are added together, that splits into a product of b to the x times b to the h, right? Two things with the same base multiplied together, that results in a summing the exponents. So we're just going to do the opposite. We're going to separate them. So when I apply that law of exponents, I'm going to get b to the x times b to the h minus b to the x, all divided by h. Now, one thing we'll see here is we have a common factor in the numerator. You have a b to the x and you have a b to the x, both in the first term and the second term. So what this allows us to do is this allows us to factor. So we're going to, in the next step, take the limit as h goes to 0. We can factor out a b to the x. And what are you going to get? You're going to get a b to the h minus 1 all divided by h. Okay. The next thing we want to notice, my friends, is that this term b to the x, this guy doesn't involve the limit variable h at all. So because my limit variable here is h and b to the x doesn't involve h, this b to the x is treated as a constant. So I can really factor that out of my limit completely. So for the next line, I can write, this is going to be b to the x times the limit as h goes to 0 of b to the h minus 1 all divided by h. Okay, so let's put together what we have so far. So we have the derivative of b to the x. So far we have is equal to b to the x times the limit as h goes to 0, b to the h minus 1 divided by h. Now, I want us to take a moment to look at this piece right here, which I'm highlighting in green, this green box right here. This is just a number. Another way to say that is, in other words, this is just a constant. Okay? So when we look at our derivative, the derivative of an exponential function with base b is basically the same function itself times a constant. And in the next video, we're going to look at a special case of this, or actually I'll just tell you right now. So there is a base b where the limit as h goes to 0 of b to the h minus 1 divided by h is equal to 1. That magic number, where when I plug in that number in for b so that I get 1, that magic number is the number e. So when the base b happens to be equal to some special constant e is approximately equal to 2.718. It's an irrational number that goes on forever. When that occurs, then we know that the limit as h goes to 0 of e to the h minus 1 divided by h is equal to 1. So in that special case where b is actually equal to this special constant e, we could say the derivative of e to the x is just e to the x. And this is one of our most important derivatives. So I'll put a little box there and maybe I'll highlight it in like this to illustrate its importance. This is one of the two functions that's its own derivative. So e to the x, the derivative e to the x is e to the x. And can you guys guess what the other function is that is its own derivative? Maybe I'll share that information with you on the next video. All right, everybody. That's it for now. Take care.